Now, who's ready to hear some outstanding research happening on our very own campus? So, our first speaker is Kendra Mclaughlin. Kendra is a fourth-year PhD student in interdisciplinary neuroscience. Her presentation title is Boldly Going Where No One Has Gone Before, a novel approach to examining metabolic processes in the brain. Kendra.
I've always found the intersection of both science and fiction to be one of the most mesmerizing forms of art. From tinkering with the delicate balance of time travel to venturing into a great unknown galaxy, anything seemed to be possible. It was in this realm where I witnessed the first African-American woman, Nichelle Nichols, play the role of a space traveler in the iconic series Star Trek. As a young girl, watching someone that looked like me do extraordinary things opened my mind to what and who I could be. Years later, I found myself embarking on my own sci-fi adventure and boldly going where no man has gone before. Or at least no one in my family. I was admitted into UNLV's neuroscience PhD program, and it wasn't until after I began my own research on the brain's ability to produce energy that I saw that the line that separated science and fiction wasn't as definitive as I had once thought. Hi, my name is Kendra Mclaughlin, and today I have the pleasure of navigating us on a sci-fi adventure through the brain. Now, some of you may still be a little skeptical as to whether energy dynamics of the brain are as cool as what we might see in a movie. Well, I'm here to tell you, they are. For instance, in the 1999 film Star Wars Episode 1, they mentioned something called Mitochondrians. It was a microscopic life form that lived in symbiosis with a host and an important component to detect the energy field known as the Force. In the film, one could actually measure the level of mitochondrians within an individual to see how strong they were in using the energy field. The Force, zoom, 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 is defined as an inner source of energy that powers all living things. And this is true for each one of us. The concept of a small organelle providing power doesn't just exist in Star Wars, but in the everyday life cycle of eukaryotic cells that make up all plants and animals. Yes, ladies and gentlemen, mitochondria, you know, the powerhouse of the cell. It's a small organelle that supplies fuel to meet cellular energy demands in the brain. Disruptions in mitochondrial dynamics have been implicated in many neuroinflammatory diseases of the brain, like multiple sclerosis, ALS, or Parkinson's disease. Lack of effective treatment options highlights the need to reevaluate disease physiology in order to find novel therapeutic targets. Much of what we know about mitochondrial dynamics highlights the role of neurons. However, the metabolic impact of immune cells like microglia that are the first line of defense in the brain has still so much to be explored. This ultimately led me to ask what is happening to the mitochondria activity inside of microglia during disease states in the brain. To measure this, I will be looking at the mitochondrial membrane potential, or the MMP. Now, similarly to measuring the level of mitochondrians within an individual, I've come up with a clever way to measure the activity of mitochondria inside of microglia. To do this, I've obtained living brain tissue from specialized mice that have glowing green microglia. And I've added on a fluorescent dye that allows me to see changes in mitochondria activity. I placed it all underneath my microscope, and there I administered a toxin called LPS to create a disease state in the tissue. And in my first adventure, I wanted to see if there were any mitochondrial differences between neurons and microglia during disease. And what I saw was after the toxin was introduced, the microglial MMP had a significant increase that happened at 3 different time points. And it would happen much more dynamically in microglia, represented in green, than in the neurons, represented in blue. I had to take a closer look at each of these time points. It was way too cool not to. And what I saw was remarkable. The microglial MMP seemed to be moving. It was moving from the body of the cell all the way to the fingertips, also known as the end feet. I wanted to see if there was a way to somewhat rescue these cells that were under attack by adding a neuroprotective drug. And to my surprise, It worked. I was able to see a decrease in the microglial MMP at every region of the cell. Together, these results suggest that microglia might have their own signaling processes located at the end feet, and perhaps make this protocol a novel way to screen other neuroprotective drugs for inflammatory diseases of the brain. I never could have imagined that my innate love and curiosity for sci-fi adventure would have paralleled the captivating world of neuroscience. As I progressed through my graduate journey, the awe and excitement I once felt watching space travelers maneuver the stars is the same feeling I get when maneuvering my microscope. The ultimate goal of my research is to advance the way we understand energy metabolism in the brain and to use this knowledge to earlier diagnose neuroinflammatory disorders. And perhaps, along the way, inspire someone else to boldly go where no one else has gone, just as I once was. I'd like to thank Dr. Dustin Hines, Dr. Rochelle Hines, the Hines Group, and all of you for your time.